This is a video about turning data center and IT industry waste into usable or reusable components and modules for other projects. It's a lot of talking. I have it broken down into chapters so you can jump to the part you're interested in, and take a look at the links in the description if you're just here for information. So these are power strips, power data units, PDUs, from data center or other IT environments. These particular ones have relays that control each outlet so they can be power cycled, turned on or off remotely. These are all dead, and I've ended up with a pile of them. I end up ripping out all the guts and turning them into static power strips like this. You can see that the guts are ripped out of this. And they're useful in my home setup, and we also use them around the shop as static power strips like this, mounted underneath benches. This one's mounted to a bench that we can move around, and next to benches like this where we have all our chargers plugged in, and over benches where they just provide convenient power everywhere. However, ripping out all those guts and turning them into statically always-on corded power strips has some side effects. The main one being that I end up with a box full of all the guts that are ripped out of them. The only things that are reused are the casings, the metal housings, the strain relief that clamps the new power cord, and all the outlet strips themselves that I punch new wire down into. But we end up with a pile of these relay boards that I've always wondered if something can be done with. And the time has come while cleaning up the shop to figure out either do something with these or throw them all out. So let's see what we can do with them. Real quick, I'm going to just show how this would work if they weren't dead. I have one working example that I purchased for my home educational lab environment about 15 years ago, secondhand. I used to use it to control groups of network devices so I could turn power on and off without having to recable everything. I had things mapped to groups so I could turn sets of devices on depending on what I was doing, and also just gaining some experience as a young professional in this industry in this kind of hardware that would show up elsewhere. So there's nothing really fancy here, but prior to integrated controllers for this kind of hardware power management on servers and equipment that we have today, this ability to power cycle things remotely is and especially was very valuable, as well as seeing things like alarms for if you're over the expected power draw at risk of loss of redundancy due to load increases or other conditions. And the big one is obviously being able to control these outlets. And you can set schedules, you can configure them in groups, you can turn outlets on and off individually. This can be done through the web interface, through command line interfaces, through SNMP, which is a UDP-based network management protocol. And that's really all there is to it. Basic monitoring and control. Within each of these three products, there are three types of modules, and they might be in slightly different form factors, over time and based on the physical layout of the device. We have the power input module, which has three main sections to it. The current transformers down here measure the input power on, in this case, three different phases for the product this came out of. And then two different, what I'm guessing are switch mode power supplies. I'm not an expert in this area, but that's likely what I'm guessing this is. So one of these is probably generating 5 volts and one is probably generating 24 volts. The 5 volts is used for all kinds of control and microcontroller logic within the unit. And then the 24 volts ends up being used for switching the relays. Then you've got this double stack board here, which is the main control unit, or has the microcontrollers that host the little operating system that supports the web server, the FTP server, the SSH and Telnet, SNMP, all those things we just saw in the web interface that are configurable, runs on this little board or stack of boards. It'd be interesting separately to see if this died or if the power supplies died. And I wonder if if this is made of generic hardware, maybe there's something else that can be done with this. And then the subject of this video is the three banks of outlets that can be controlled through these relay boards. When I was taking these apart and realized that they were just 3 of the same board with a ribbon cable that connects them together, it started to feel like this might be something that could be used. And with the generic 1/4-inch terminals used for the inputs and outputs, this could be put into some housing or mounted on a board and used for all kinds of interesting little projects. So within the board, I've identified that it's broken into 9 sections. This section down here has the I2C input-output module, 2 quad NOR gate ICs, and then 1 kind of functional block per relay, per switched output. And you can see the repetition on these. The relays switch directions, so the symmetry changes on some of this as you go down, or symmetry alternates. And then you've got another 10-pin header up here where it daisy chains out to the next module. The switched outputs are completely independent. I suspect that's, so that is there's no bus under here connecting phase A to A to A. It was done by jumpering off the wire that came across this. Actually, I have an example of that. So this is how the 3-phase ones are constructed, with the three phase conductors coming in, and then every third terminal is tapped into the same wire. So we can see black, black, red, red, red. This works to our advantage because this ends up being 8 completely independent functional units. We aren't handcuffed by having there be, every third one being connected together already. You certainly can do that by reinstalling whatever wiring you want. Same with Let's talk about working backwards to figure out, as somebody who is not an electronics expert, how we can talk to this I2C 8-bit input-output driver and start controlling these. Now, what some of the pinout is for this header to start talking to this thing. The manufacturers and exact model numbers of these components vary, but the function and the pinout is the same. This one is the I2C device that we will be immediately talking to, which is a PCF 8574 remote 8-bit I/O expander. The one I was first looking at was a Texas Instruments. This is the data sheet for it. And what we're after is the pinout. We have this package here, and we'll overlay these lines onto this drawing. We end up with something like this. The first 3 pins are the address lines that set the address that this will respond to on the I2C bus. Then we have our first 4 output pins, or I/O pins, ground, the remaining 4 I/O pins, an interrupt pin that would be used with a microcontroller in different applications, our I2C clock and data lines, and VCC, which in this application will be +5 volts. Right away, we are able to work from the data sheet of this, and using the multimeter in a diode check or resistance mode, trace out these 3 pins and ground over to this header. We find out that there's 2 common tied together ground pins. They're also attached to the ground plane of the board. Our I2C clock and data lines, and our VCC +5 volts. Now, if we tone out from the output pins to the next chipset, we can figure out what's what there. The next chip here is a quad dual input NOR gate. Looks like this. We'll talk about how this is being used in a minute. We can see the pattern of pins is output, input, input on this bottom row of pins, and then input, input, output on the top. So if we overlay those, I forgot to mark ground here, but we have VCC on the last pin, ground is over here, and then the I/O pins of the expander map to the second input of each NOR gate as shown here. So the bottom chip is 0, 1, 2, 3, 4, 5, 6, 7. If we tone out more of this, we find out that the first input of each NOR gate goes to ground. So this functionally is using each NOR gate just as an inverter to invert the output of the I/O expander My guess at why this is done is because this chip comes, its default state is with all outputs enabled, and so they invert it so that all the outputs are disabled. So then we mark this up a little more, and we can say, okay, every third pin is now an output here, an inverted output of the I/O expander. So we've got outputs 0, 1, 2, 3, and so on. Toning a little further, we find that so the nearest functional block, relay control block, is number 7. So output 7, toned from one of the coil legs. This relay has a constant 24 volt source to one leg of the coil, and it is ground side switched through this NPN transistor. The emitter leg goes to ground. The input or base leg here is output 7 from the inverter, and then the collector here goes to what would be the ground side of the coil. So when this output pin comes high, it enables the path from the coil to ground. I don't know exactly what the other transistor here is doing. Maybe it controls the LED or something else. And then one other note is, if you measure the resistance from here or try to trace this out, diode check mode may be misleading. You would want to use resistance check, and you'll find that there's a 2 kilo ohm resistor here. So this is going output 7 through the resistor to the base leg of the transistor. So we finally end up with this. One end of the coil always has 24 volts coming in from these middle 2 pins on the header. The other end is ground side switched through the transistor as explained. So this ends up being our final header pinout for everything we need to control the relays. So let's put it all together. We have a Raspberry Pi hooked up with colors that should be the same as what I had in those pictures I was marking up with the pins. So orange is VCC, we're getting the 5 volts from the Raspberry Pi. Yellow is our data line, green is clock, black is ground. These red and black alligator clips are 24 volts from a bench power supply. We're tying that ground together. So we know from the pinout that we made that the 2 ground pins in this jumper are common at the board. So I have one of those going to the 24 volt power supply and one going to the Raspberry Pi to reference the 5 volts and the 24 volts to the same ground. I'm using one of the ribbon cables from the original unit to come over here. And I have a loop running right now that's just toggling pin 3 every 2 seconds. And I actually have this daisy chained through to another board, which apparently is using the same address because it too is cycling pin 3 right now. I don't know exactly how the addresses are set on these. All the ones I've touched seem to be set to address 20 in hex. So there must be something else about the install. Maybe it's, I haven't traced out the address lines to figure out how the address is set. So I've got 24 volts being supplied by this power supply here. And then this is the loop I just have running right now. And I'll share some code in the description that some of the detail about what library is being used here to talk to this. This is all right on theme with something I enjoy doing, which is fixing things that are heading to the trash that nobody thinks is worth fixing, or figuring out how to extract value, reuse parts from things. In this case, it's an entire subsystem that has value. And in other cases, we just learn from it. I don't have a ton of electronic skills. Being able to reverse engineer something even this basic is an enjoyable learning experience for me. And who knows, what else there might be to do from this. Maybe the ROM or the application on this can be flashed easily. I know it has a mechanism built in to flash new firmware, but somebody who's into low-level hacking and embedded systems kind of programming potentially could do all kinds of interesting things with this if they reverse engineered the format of the firmware that's loaded to just load a new image in. I highly doubt it's cryptographically signed. or figure out which of these ICs on here stores the application data and potentially be able to flash it right into there, sidestepping any checks in the current software. I don't have a video on turning the PDUs into static power strips, but I do have a long form write-up I did a few years ago that I'll share a link to in the description as well. Thanks for listening to me talk about this. You will see me in the next one.